It's time for some more megaprojects. Specifically, this could change science. Could cold fusion replace nuclear energy? Presumably implying that fusion is somehow not nuclear energy. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuke, but I can certainly share some knowledge. Let's see.
Every few decades, science stumbles across something that sounds impossible but refuses to go away. The details might be disputed, the data might fall apart, but the idea lingers. Wait.
Well, that's because a lot of those have powerful incentives, such as limitless clean energy and ambiguous experiments, which in nuclear engineering, ambiguous isn't good enough. Nuclear reactions leave behind unambiguous footprints. That is to say, specific radiation and isotopes. If those aren't there, then a reaction didn't happen.
Waiting for another chance. And cold fusion, well, that's one of those ideas, isn't it? In March 1989, two electrochemists from
these fine gentlemen here. If you want to hear a much deeper dive on the exploits of these two, I'll pin that video in a comment.
University of Utah, Stanley Pons and Martin Fleischman stood in front of reporters and made a claim that caught everybody off guard. They said they'd just triggered a nuclear reaction in a laboratory using heavy water and a palladium electrode.
Classic example of a huge claim without enough reproducible experiments to validate that claim.
The process took place at room temperature without radiation, and it produced more heat than they could explain.
That right there is the red flag. Deuterium loaded into a palladium lattice, producing excess heat, and they attributed it to nuclear fusion. Problem is it didn't leave behind any nuclear signatures, such as neutrons, tritium, helium isotopes, gamma radiation, at a rate that would be consistent with true deuterium-deuterium fusion.
If the claim was accurate, the implications were absolutely enormous. It meant nuclear power without reactors, without high temperatures. Really importantly.
Okay, couple of red flags. Room temperature fusion directly contradicts the known Coulomb barrier between nuclei, as in what it would actually take to cause fusion. And no radiation, if you're producing several million electron volts per reaction, like a true fusion reaction, say in the sun, it's not going to be useful. The whole point of having a reactor is you need that bulk, high temperature system to generate enough heat to spin a turbine, spin a generator, generate electricity in large amounts. Even if this thing somehow worked, if it's produced so little energy, it wouldn't be particularly useful. I mean, after all, real fusion produces energetic neutrons and activation products. Saying it didn't leave behind any radiation or any radioactive waste just isn't a safe assumption. Just like anything else, it's going to generate waste. Unless they somehow used an unknown part of physics or magic or whatever it is they're trying to do.
Without radioactive waste, it suggested that clean, abundant energy could be produced using equipment that fits on a table, not in a power plant.
And that's where all the hype started.
For a few weeks, the news cycle ran wild. Newspapers called it a scientific revolution, investors showed up, and political leaders started to pay attention. Then, the replication efforts began.
And any scientist is going to warn against doing something like that before you get repeated results.
And the results, not exactly encouraging. You probably knew that, given that we're not all just using cold fusion today. Most labs could not reproduce the effect. Leading physicists expressed doubt almost immediately, and within months, the story shifted from triumph to embarrassment. Yep. Cold fusion became a warning about
confusion,
poor experimental controls, and premature publicity. But even as the headlines faded,
this really is a case study of don't publish your thing too quickly without getting repeated results.
A few researchers kept working quietly. Some of them reported unusual results that never made it past peer review. Others claimed to measure heat that they could not explain.
That's true, there's still a small community out there, but anecdotal, non-peer-reviewed reports just don't mean a whole lot.
Over time, the phrase cold fusion was replaced with something more cautious: low-energy nuclear reactions, or LENR.
Have to rebrand it.
Fast forward to 2025 and the conversations started again. This time, it includes military labs, government grants, and serious scientists who believe the topic deserves another look. There is still no consensus, but there is no longer universal dismissal either.
Is it just me, or is he a little more, I don't know, he seems to be a little more into the whole ASMR triggering narration. Kind of reminds me of some shows on NPR.
So what exactly is cold fusion? Why did it attract so much attention? And why did it fall apart so quickly? And most importantly, is there any reason to believe that it might actually work? Well,
so only if a rigorous, blind, independently reproducible experiment shows excess heat significantly above chemical energy bounds and corresponding nuclear products at rates consistent with the energy released during the fusion reaction. And to date, those two boxes have not been reliably ticked.
Let's go back to where it all began. The promise. Cold fusion proposes something extraordinary, a nuclear reaction that happens near room temperature. Unlike traditional fusion, which takes place in the heart of stars and inside experimental reactors using ultra-hot plasma, cold fusion would occur in a small lab environment with no massive heat, no glowing chambers, and no radiation burns, which is nice for the scientists. That contrast is at the heart of its appeal.
Yeah.
Now, traditional fusion forces atomic nuclei together by blasting them with energy. You need magnetic fields, vacuum systems, and machines the size of buildings. And even then, most experimental reactors consume more energy.
What's interesting is the sun has comparably cold fusion at a temperature of merely 15 million degrees Celsius compared to the temperatures in excess of 100 million degrees Celsius you need on Earth. And that's just because of sun's high gravity. It can get away with self-sustaining fusion reactions at a relatively low temperature because its gravitational force is so strong.
Than they produce, which isn't much good at all. Fusion works, but scaling it for energy production has proven slow, expensive, and unpredictable. Cold fusion suggests a shortcut. That begins with hydrogen, often the isotope called deuterium, absorbed into a metal such as palladium. As the hydrogen atoms settle into the spaces within the metal structure, something unusual may happen. Some researchers believe that under the right conditions, the atoms interact in a way that produces heat. This heat, they claim, is far greater than what could come from ordinary chemistry. What makes these claims intriguing is that in some experiments, the excess heat appears alongside helium or trace particles that hint at nuclear reactions. However, these reactions do not release the harmful radiation one would expect. That gap, the presence of possible nuclear effects without typical nuclear side effects, is what continues to puzzle researchers.
So what can happen in this electron screening in a metal lattice with something like palladium can modify the absurdly low probabilities of tunneling, but not by factors of several million that would be needed to cause fusion. And it would have to produce radiation. Fusion produces radiation, which is a good thing. Otherwise, the sun wouldn't take care of us very well. The nuclear signatures have to be present.
Now, if the effect is real and can be understood, the consequences would be far-reaching. It would mean energy production without smoke, fuel combustion, or waste byproducts. It would require no uranium.
In other words, some sort of crazy 100% efficiency sci-fi reaction that has never been seen through any forms of power generation, not just nuclear.
No radioactive decay, and
no, fusion wouldn't involve uranium at all either. I mean, good luck trying to fuse uranium. It's a big one. It's the one you want to split and use in a fission reactor. You shouldn't be anywhere near uranium on your periodic table when doing fusion, cold or otherwise.
Massive turbines. Instead of needing a grid fed by power plants, each home or building, in theory, could become its source of power.
Okay, so not only are you saying we're going to do away with a big nuclear plant as your heat source, we're just going to do completely away with power plants altogether. And this was going to be the equivalent of having solar panels in your house or something like that, just with cold fusion. All right. And presumably that's also 100% efficient, just putting all your house loads up to this thing. No need for maybe having a fusion battery or a little cell.
Energy infrastructure would shift from centralized megaprojects to small, efficient systems that serve local needs. This has implications beyond cost or convenience. Cold fusion, if proven, would upend existing assumptions about energy security.
All right, so even if it did work the way you claimed, saying it's going to you're going to get rid of large-scale energy production and just everyone's going to have just their little cold fusion thing at home? No. I mean, people have modular solar and even in some cases modular wind for their own house. But that hasn't done away with large-scale solar and wind production just because of how economies of scale work. That I don't even see the reason to go there, but I can kind of understand some of the hype during the Fleischmann and Pond days. Maybe that's what he's referencing.
Development planning and international competition. Countries with little access to fossil fuels or nuclear facilities could generate energy independently. Climate targets would be easier to meet.
That assumes they have access to whatever magic you're working with in this cold fusion experiment. So apparently that needs to be evenly checked between all country. Whoever set up the Earth checked the strategic balance icon for cold fusion before starting their game of civilization.
Not painful trade-offs, emergency power systems could become far more reliable, far more compact. The materials involved, they're not rare. The setups, if viable, would not require billion-dollar investments. Instead, power could be drawn from devices the size of a suitcase, or smaller, with few moving parts and no emission.
All this is fantasy.
Use cases for rural hospitals, disaster.
Even if cold fusion somehow worked, this is just kind of a whole different thing. Not only does the technology work, but this vision for miniaturized power sources for everything. I mean, it's possible for you to have situations like this, but it wouldn't be used by everyone.
Zones, space stations, and underwater operations, just anywhere that the traditional grid just can't reach. The science here...
Okay, it would be helpful where the traditional grid couldn't reach, kind of like RTGs, radioisotope thermoelectric generators, are used for things like space probes and remote Arctic weather monitoring equipment that you just don't want to send someone out to connect it to the grid or replace it very often. That makes a little bit more sense.
Remains unsettled, but the potential scale of the reward is what keeps interest alive. Few ideas offer a return this large for an investment this small, if it works. That is the reason
if it works.
Cold fusion hasn't disappeared. It explains why some scientists continue the search, and it shows why the announcement in 1989 triggered such an overwhelming wave of excitement. People were not responding to the hype, they were responding to the scale of the promise. After the announcement, the momentum kicked in. Cold fusion made headlines around the world, with major newspapers calling it the most important scientific discovery since the splitting of the atom. Cameras followed the two chemists from lecture halls to TV studios. Journalists asked whether it would solve the energy crisis. Commentators speculated that oil and coal might become obsolete within a decade. The idea caught.
There you go. Keep saying it's 10 years away. Even if it was, it wouldn't obsolete anything that quickly, and maybe keep saying it's 10 years away so you can keep your funding up.
Far, not just because of what it claimed, but because of how much it seemed to promise. A low-cost, clean energy source that could be built on a lab bench. That was really hard to ignore. But inside the physics community, the mood was different. Physicists who worked with fusion...
I like that it was inside the physics community, implying that people who actually know things about physics know this is a scam.
Every day were skeptical. Fusion, as they understood it, came with unmistakable signs. It gave off gamma radiation. It produced neutrons. It left clear, often dangerous footprints.
So it's interesting. So cold fusion, if it did work, it also wouldn't be anything like nuclear fusion if it didn't release any sort of fusion-based heat without nuclear reaction.
The Utah announcement mentioned none of this. There were claims of heat, yes, but no hard numbers, no nuclear signatures.
And the thing is, those numbers are pretty well known. After all, if you're doing deuterium-deuterium fusion, it's going to release about 4 MeV per fusion, which figures out for per watt about 1.6 times 10 to the 12th power fusion reactions per second. which would correspond to a neutron flux of about 8 times 10 to the 11th power neutrons per second. Say half of the deuterium branch goes to the neutron branch, and that emission rate would produce, even on a small setup, a very large, easily measurable neutron flux. Neutron detectors would go off, gamma detectors, you'd be able to tell it just by having a Geiger counter.
Immediately raised questions. In labs all around the world, scientists began to test the idea for themselves. Universities and national labs attempted to recreate the experiment. Some had access to similar materials, some even spoke directly with Fleischmann and Pons. The early attempts were promising enough to keep going, but as the replications increased, the results became harder to defend. Many labs found nothing. Others measured small amounts of excess heat but could not rule out measurement error. Some teams saw fluctuations that seemed interesting but never appeared again. The effect was inconsistent and fragile. There was no clear recipe, no pattern, and no way to tell when or why it might work. Without reproducibility, confidence collapsed. And then came the public response from governments and academic institutions. The Department of Energy organized a special panel to investigate. Scientific journals declined to publish the original data, citing a lack of peer review. Physicists
Again, if you want to see my full thoughts on the scandal behind all of this, please click the video in the linked comment.
criticized the decision to go public before the science had been vetted. The announcement had skipped every normal safeguard. That looked less like a discovery and more like a publicity stunt. As the scrutiny deepened, more problems surfaced. The experimental setup lacked proper calibration. Control experiments were missing. Some of the reported heat may have come from chemical reactions and not nuclear ones. The instruments used to measure temperature.
All just implements of just sloppy science. No control groups, no isolating the source of your experiment.
Were not accurate enough to detect the small changes being claimed. The theory behind the reaction was
even back then, instruments were pretty sensitive, so claiming they weren't accurate and they're not detecting any source of radiation, it's simply because they weren't making any, as in this wasn't fusion.
vague at best. Then, the entire case began to unravel. Within months, the story had reversed. Media outlets that once praised the announcement were now highlighting the backlash. The same journalists who called it a breakthrough were asking how such a mess had made it to national headlines. The shift in tone was harsh because public interest disappeared and research dollars vanished. By the early 1990s, cold fusion had become a cautionary tale. Fleischmann and Pons, once celebrated, were now avoided. They continued to defend their results for a time, but stopped making public appearances. Scientific conferences would not host cold fusion panels, and major labs stopped investigating. The term itself became a punchline in some circles. To most of the academic world, the case was closed. Cold fusion had started as a possible revolution. It ended, at least for the moment, as a warning about rushing science into the spotlight before it was ready.
And that's essentially the lessons that I learned about it when I even remember it as a case study in physics classes that I took in undergrad.
Even after the collapse of cold fusion's reputation, the idea didn't completely disappear. While most of the scientific community moved on, a handful of researchers continued the work. They tested small setups, refined their methods, and collected data. Their labs were underfunded, often overlooked, and rarely part of any major institution. But the experiments kept going. And what they found was not proof, but it was not nothing either. From time to time, they recorded temperature increases that did not align with known chemical reactions. The setups were often similar: palladium electrodes soaked in deuterium, monitored for changes. And in many cases, the heat levels were minimal. But in a few cases, the results were strange enough to prompt further testing. Because the term cold fusion had become a scientific red flag, these researchers began referring to the work with a new name: low-energy nuclear reactions, or LENR. It was more neutral, more descriptive, than it left space for uncertainty. Rather than claiming a breakthrough, it referred to a collection of unexplained observations that might involve nuclear behavior.
Sure.
For many years, LENR research remained on the margins. Peer-reviewed journals rarely published it. Funding was difficult to secure. But a slow shift began to take place. By the early 2000s, a few government agencies started paying attention. The US Navy and DARPA supported small investigations into LENR-related heat effects. These studies focused on understanding whether the observed signals were real and what mechanisms might be responsible. Laser stimulation, metal loading ratios, and isotope measurements became common areas of focus. In Europe, interest emerged through research frameworks like Horizon 2020. Projects like Clean HME, based in Poland, brought together universities and private labs to study LENR phenomena using improved tools. These efforts emphasize better calibration, more rigorous data collection, and an emphasis on eliminating noise. In Japan, university labs received backing from tech companies to conduct controlled experiments on hydrogen absorption and thermal anomalies.
So, some things that can happen that can generate heat that have nothing to do with fusion associated with this experiment. As simple as electrochemistry, recombination, hydrogen absorption or desorption, corrosion, or instrument calibration issues can generate heat or spurious signals that could look like excess energy. But without a radiological signature and without the energy needed for fusion, it isn't fusion. I mean, I can understand getting excess heat from an experiment, but thermal energy at room temperature is 0.025 electron volts, which is more than a factor of 10 million smaller than what you would see for a deuterium-deuterium fusion reaction. So unless you're seeing heat generation that's that much bigger, it isn't fusion. And that's probably for the best, because heat energy in these little experiments, some of these pictures, some of these little setups without putting things in place like radiation shielding, that's going to be hazardous to your health, to be exposed to even a modest neutron flux. Not the same neutron flux that you would see in a nuclear power plant, but neutron doses scale higher per unit of energy compared to, say, gamma radiation, at least as far as the dose's effect on the human body. It's 5 times more for a slow neutron and 20 times more for a fast neutron. And any fusion at scale, just like any fission of scale, you're going to have a spectrum of both. How much depends on the reactor design.
In the United States, ARPA-E began allocating funds to investigate possible LENR signatures in solid-state systems. Now, these experiments were tightly focused. They were framed as inquiries into basic physical mechanisms, rather than chasing energy.
I don't have a problem with people asking questions, though, for further understanding about heat generation. I don't have an issue with that at all, but claiming it's some crazy energy source and you're doing fusion, that's specious at best without the evidence of radiation.
Applications researchers aimed to understand if nuclear-level interactions were possible under low-energy conditions. The outcomes were cautious, but the interest was real. By 2025, LENR was still far from mainstream, but it had carved out a narrow space in scientific inquiry. It existed in small labs, in specialty conferences, and in government-backed programs that preferred to ask questions rather than declare conclusions. The headlines were gone, but the experiments had never fully stopped. And slowly, the field began to rebuild its footing, one cautious paper at a time. The evidence. So far, the strongest recurring observation in LENR research has been the detection of excess heat. These experiments typically involve palladium or nickel lattices loaded with deuterium or hydrogen. Under the right conditions, some of these systems generate more thermal energy than can be explained by chemical reactions alone. The results vary widely in strength and are not always repeatable, but even so, the number of reports—
That's just it, they're not repeatable.
over the years has kept interest alive. In some cases, researchers have measured small amounts of helium, minor traces of tritium, or subtle shifts in
small amounts of helium, tritium. Again, you're just orders of magnitude short to explain it via nuclear fusion.
Isotope ratios. These are possibly nuclear byproducts, and
the numbers I've heard were on the order of single-digit to double-digit electron volts, which is more than what you'd expect, but not the millions of electron volts that would truly fingerprint this.
Sometimes accompany the reported heat. However, the signals are often faint, and independent confirmation has been difficult. At the same time, another detail remains puzzling. Traditional nuclear fusion releases high levels of neutron radiation. LENR experiments, in contrast, show neutron levels that rarely exceed background readings. That gap continues to divide opinion. The presence of heat and helium suggests a nuclear process could be involved, but the absence of neutron radiation makes that conclusion harder to defend.
Yeah.
For many physicists, this mismatch remains a barrier to acceptance. Despite the doubts, research continues across several countries. At MIT,
It's all about you have to see the right quantity of helium, the right quantity of tritium.
scientists have used calorimetry to study deuterium-loaded palladium cells. Their experiments focus on eliminating error margins and testing for repeatable patterns. In Japan, Clean Planet and affiliated university groups have partnered with private companies to examine small LENR devices. These teams are working in carefully monitored conditions using advanced detection tools and strict protocols. In Europe, the Clean HME project remains active under the European Commission's funding structure. Their objective is to explore the physical mechanisms behind LENR-like effects. They are not developing reactors. Instead, they're running controlled tests with improved instrumentation, including neutron detectors and isotope analysis tools.
That's a step in the right direction, having the right instrumentation and controls when monitoring your experiment.
United States, the Army's Cold Regions Research and Engineering Laboratory has taken a particular interest in LENR systems. Their work involves hydrogen and palladium setups, simulated with lasers and observed using high-resolution monitoring.
You could tell the Nuclear Regulatory Commission isn't taking it as seriously because they're not classifying these as reactors, because they know they're really not. They're just small-scale experiments.
These projects are supported by internal Department of Defense funding and are designed to remove ambiguity from the measurements. Meanwhile, several companies have moved into early-stage development. ENG8 in the United Kingdom, Orion in Canada, and Prometheus in Italy all claim to be building LENR-based energy devices. Most of these involve nickel and hydrogen systems. However, few have released peer-reviewed data, and most remain in prototype form. As of 2025, the call for renewed investigation is gaining momentum. Brian Josephson, a Nobel laureate in physics, has repeatedly supported LENR research. He and others from institutions like MIT and Cambridge have signed public letters encouraging further inquiry. These appeals do not...
It could just encouraging further inquiry, could just be a matter of let's put this to bed once and for all, because everyone kind of gave up, and this could just prove once and for all that it doesn't work.
Claim that LENR has been proven. Instead, they argue that the observed anomalies are too consistent to dismiss outright. The mystery remains unresolved, but the recurring signals, the slow expansion of interest, and the gradual return of institutional support all points to the same conclusion. While science is still far from settled, the question's no longer ignored. And even with all the skepticism, a few theoretical paths have remained open.
I'm not sure what's actually driving the renewed interest in it. I think it just has to go back to the alleged promise of having a really abundant source of clean energy without as many of the drawbacks, allegedly. Ultimately, even if it did, energy does not equal infrastructure. And it wouldn't help, say, with transportation, for instance, or any heavy industry that involves mass use of chemical feed. There would be manufacturing bottlenecks. You're still going to need massive, I guess, fusion cells to store your energy. So just being able to generate it by itself, that's a bit of a reach, but it doesn't.
One of the most discussed models is muon-catalyzed fusion. Now, in this scenario, a muon, which is similar to an electron but heavier, replaces an electron in a hydrogen atom. Because of its mass, the muon brings the atomic nuclei much closer together than an electron would. This proximity increases the
energy with an
fusion
exclamation
without
point.
requiring extreme temperatures. The effect has been demonstrated in laboratory settings since the 1950s, but it's never been practical. Muons are unstable particles that decay quickly and
So ultimately, you're going to lose more energy. We're talking on the orders of giga electron volts per muon, whereas previously we've been talking in terms of mega electron volts per fusion, which is energy output more than a factor of 1,000 less than energy input, which puts us in a similar problem that regular nuclear fusion has, which is an interesting experiment, but it's not a practical energy source, and it's just a little different. I mean, how this works is it shrinks the electron cloud, increasing the probability of fusion.
Producing them in sufficient quantities requires more energy than they could generate through fusion. That energy imbalance makes muon-based fusion unsuitable for real-world power generation, despite the elegance of the concept. Because of that limitation, most of the serious interest in recent decades
Muons are pretty exotic.
has turned towards solid-state systems. These studies focus on what happens when hydrogen or deuterium is loaded into certain metals, especially palladium or nickel. These metals can absorb large volumes of hydrogen atoms into their crystal lattices. When this happens, the hydrogen atoms become densely packed inside the metal, held in place by its internal structure. Some researchers believe that under specific thermal, electrical, or magnetic conditions, the arrangement of atoms within the lattice could create a low-energy environment where nuclear interactions are possible. The reason this attracts attention is that the metal lattice might reduce the natural repulsion between atomic nuclei. In normal conditions, two positively charged nuclei push each other away, which physicists call the Coulomb barrier. But in a solid, tightly packed structure, something quantum effects may allow atoms to tunnel through this barrier more easily, creating rare opportunities for fusion-like behavior.
But the probability is so low it's still essentially zero even at scale.
This is not conventional nuclear physics. The theory here is that the metal lattice...
Saying it's not traditional nuclear physics implies that it's just not working, because claiming you're making new physics just so your device would work versus not, that just doesn't make any sense.
Does more than just hold the hydrogen. It may cause collective quantum effects that allow the atoms to behave differently than they would in gas or plasma. These effects might lower the barriers that usually prevent nuclei from getting close enough to fuse.
And again, it does increase the probability, but not by enough that you're going to have a self-sustaining fusion reaction.
In traditional fusion, overcoming this barrier requires extremely high temperatures and pressures. In LENR experiments, the idea is that the metal does some of the work by aligning atoms in just the right way. It is a subtle and poorly understood mechanism, but one that has generated enough curiosity to support further testing. Some research groups are now focusing on how to create these rare conditions consistently. Experiments have included using electrical currents, acoustic stimulation, and magnetic fields and thermal gradients to manipulate the behavior of the hydrogen-loaded metals. In some setups, researchers have introduced laser pulses at specific wavelengths to try and induce a response within the lattice. The hope is that triggering the system in the right way will produce a repeatable reaction that yields excess heat.
You might as well try shaking the thing to see if it works. That's essentially what you're doing on the atomic scale, whether you're using a laser or you're using a sound wave or something. It's just not reliable. I mean, how would you like it every time you start your car? You have to open up the hood, pull the engine out, give it a good shake, and then put it back in, and maybe it'll work.
While a few of these tests have shown promising data, most remain difficult to verify, and reproducibility remains a major obstacle. Another line of thinking looks at the energy barriers inside the metal structure. Even if conventional fusion is not occurring, nuclear reactions of a different kind may be taking place. These might involve shifts in isotopic ratios, small emissions of helium or tritium, or other byproducts that suggest nuclear-level processes without following standard models. Several LENR proponents argue that these rare events, even if extreme...
Okay, not following standard models. What kind? Does he mean the standard model of particle physics? Because that's its whole can of worms that if you're breaking that, then that's arguably an even bigger discovery than an allegedly unlimited energy source. But he probably is referring to standard models for generating electricity from generating heat from fusion, which, yeah. And the simplest solution is you're just not doing fusion because you don't have any radiation.
Any weak could collectively generate measurable heat over time. And if true, that would mean that energy is being released through a mechanism not yet captured by existing theory.
Look at this. All right, we're going into sci-fi territory even more.
Now, one of the most persistent challenges is the mismatch between the reported heat and the lack of radiation. In standard fusion, heat and radiation go hand in hand. You cannot get one without the other. But in many LENR experiments, the heat appears without detectable levels of neutrons or gamma rays. This matters because radiation, especially neutron emissions, is a signature of nuclear reactions. When atomic nuclei fuse, they usually release energy by ejecting particles.
These guys are probably lucky they didn't do that, because they didn't set up any of the shielding properly, so they would have gotten a nasty dose of neutron radiation if this sort of phenomena did exist.
Particles which we detect as radiation. Without those byproducts, it becomes harder to argue that the heat is nuclear in origin. That is one reason many physicists remain cautious. If energy is being released, but not through known nuclear channels, it raises the question of whether we're seeing a new kind of process or simply a misinterpretation of chemical effects.
Yeah, and the fact that it isn't reproducible makes me wonder if we're really seeing anything at all.
This absence makes many physicists skeptical. It suggests that the heat may be the result of chemical effects, measurement errors, or unknown artifacts. Still, supporters argue that we may be dealing with a new kind of interaction, one that sidesteps traditional expectations. The lack of working prototypes adds to the...
What's weird, though, is this new process, it's not consistent with what we have observed in actual fusion reactors we've been able to do on Earth, such as using tokamak or stellarator designs or the National Ignition Facility. So this would require rewriting nuclear physics from scratch while somehow leaving every accelerator and reactor experiment intact in the process. That's pretty unlikely.
Uncertainty. No laboratory has produced a system that generates continuous, reliable energy on demand. There are test rigs that have shown energy output above input levels, but these results fade quickly and often fail to appear under repeated trials.
Yeah.
Even well-funded labs with high-precision instruments have struggled to replicate promising data. That inconsistency is what keeps LENR on the fringe, even as small signs of progress continue to emerge. Still,
like what? Progress being that they're actually going to use a control group and bring in proper detectors, because that's the main difference I've seen.
Researchers in the field, they're not discouraged. Some of them believe that the problem is not the science, but the control systems. In other words, the effect may be real, but it's extremely sensitive to small changes in materials, environment, or experimental setup. And if that's true, the next step isn't a reactor. It's a better understanding of how to reliably create the conditions under which LENR might take place. That requires improved instrumentation, more standardized protocols, and careful...
That's not a bad idea.
...long-term studies that are not rushed to publication. The potential payoff remains enormous. If even a fraction of the claimed heat outputs are real and repeatable, they would represent a fundamentally new source.
And again, I rest the point of no, it wouldn't. If it did somehow work, it would be cool, but it would be in the same category as hot nuclear fusion on Earth. And that one's at least closer because they at least reliably create fusion. And it's a fair bit further down that road. And of course, the step after that would be getting significantly more energy output than energy input, and then determining how it competes against other energy sources in the market. But they've at least proved that works. Fusion does happen. Here, we're not even sure about that. So saying once we're immediately going to revolutionize the world's energy economy. Keep in mind, a lot of it just doesn't work on just heat and electricity. There's not taken into account, we're just talking are we talking electricity? Are we talking propulsion? Or for, say, cars, propulsion for ships, aircraft? Yeah, those are some pretty big gaps to overcome, even if cold fusion somehow worked and we put it in the same category as hot nuclear fusion.
Of energy. It would not be fusion in the traditional sense, but something adjacent, something that taps into interactions that we don't yet fully understand. That alone is enough to justify continued investigation.
I do appreciate low-energy nuclear reactions. Of course, that gets a bit confusing when you refer to things like radioactive decay, which is low energy, and a nuclear reaction. So its naming can be a little confusing.
In the eyes of many scientists, even those who remain cautious about making predictions, there's also a growing awareness that we may need to rethink some long-held assumptions about nuclear reactions. Most nuclear physics was developed in the context of high-energy collisions and particle accelerators. LENR, by contrast, is happening, if it's happening, within the confines of solid materials at room temperature. It's not unreasonable to think that new rules might apply under such different...
But radioactive decay happens all the time. And again, just like I just said about changing the rules and somehow high-energy nuclear physics still works, nuclear power plants still works. But nuclear power plants are in a different category. High energy is smashing things with accelerators at really high energy, like tera electron volts. Even nuclear power plants, we're talking 200 million electron volts per fission, which is high due to uranium's high energy density, but not like you're deliberately accelerating the stuff as fast as you can to run a power plant. That's not how those work.
Conditions. Several labs are now exploring this possibility with support from government and private sector funding. Basically, LENR remains an open question. It has not produced a breakthrough. It has not delivered a usable power source.
I'm still thinking it's because you're not measuring it consistently, because stuff like that is hard to detect and inconsistent.
But the combination of unusual results, plausible theories, and continued interest from serious institutions does mean
I would not call anything associated with LNER a proper theory. Maybe certain weak hypotheses, but to put it in the same category as scientific theory, just no.
that it's not yet ready to be dismissed. It sits in this grey area between physics and engineering, between what we understand.
I was going to say gray area between physics and sci-fi. It's not. There's not really a whole lot of engineering.
and what might still be waiting to be discovered. And that uncertainty makes it frustrating, but it also makes it compelling. The search continues not because it has already succeeded, but because it has not completely failed. And that's enough.
As an engineer, not getting repeated results is a failure in and of itself. Now, I'm not dismissing if someone is interested in studying LENR, please go right ahead, but just do it from the lens of you're curious about chemical interactions. You're just from a pure sense of curiosity about wanting to see how it interacts with palladium or whatever, rather than I'm got to prove it to uphold the hype or whatever, because that sort of bias going into it just isn't good for any sort of scientific experiment. And hey, I will fully accept to be proven wrong if someone does it. That would be a cool thing to be wrong about, if there really is something there and the implications for greater physics and greater engineering. I'm just not convinced yet.
To keep a small but determined group of scientists asking one simple question. Can it really work?
Verdict, no.
Now, after more than 30 years of research, cold fusion remains unresolved. It has not been proven, but it hasn't been fully disproven either. Most experts still view it with deep skepticism.
You could argue it has a very low probability of appearing to work if you just take a bunch of quantum tunneling into account, the same non-zero probability of quantum tunneling phasing through the entire Earth and entering from the other side, but not practical.
But the idea never completely disappeared. It continues to surface in new experiments, quiet funding rounds, and occasional calls for reconsideration. What makes this story unusual is not the scale of the original claim. Science often produces bold ideas that turn out to be wrong. What makes this different is the persistence of small results scattered across decades that refuse to fit cleanly into any existing theory. A growing number of respected scientists have said it is time to take another look. They are not promising success. They are not saying,
I don't know. To me, that sounds like an appeal to authority. I'm going to be cautious about that. They could just be interested in it for other reasons. Who knows?
cold fusion will work. But they believe the question has not been answered yet. And they argue that ignoring unexplained data simply because it comes from a controversial field does not reflect good science. The logic's simple. If the effect is real, it deserves careful study. If it's not, then testing it again will help close the question with confidence.
That's fair.
Either way, progress comes from evidence, not from reputation. LENR research still faces serious challenges. The data's inconsistent, the theories are incomplete. No working device has been built. But if it never works, well, then it belongs on the list of the most curious and stubborn scientific questions of the last century, a mystery that refused to disappear, even when nearly everybody stopped looking.
I don't know, when I clicked on this, I was expecting if there was some idea, if there was another Pons Fleischmann emerged, even if it was another crackpot experiment, but this just kind of seemed like a rehash of stuff from 35, 40 years ago, so I don't think a whole lot of progress has been made. Thanks so much for the recommendation. Thanks so much for watching. I'll see you next time.